Okay. Is this working now? Oh my god, it is. Yo. Yo, check this shit out.
It's got a lag.
Well, of course it has a lag, but it works. What? Okay, you should move over one.
Alright, welcome to the organic chemistry review, everybody.
Yeah.
I'm not need to move over here. I need to charge it.
You're only 4 semesters away from that, some of you.
Or you could move here, or you could move like.
faster than you think.
I'm gonna sit behind you so that you have room for this entire row.
Okay.
Why don't you sit here? Have the thing balanced here and I sit here.
I mean, if that's the case, then you could sit here.
True.
Let me see if I can get a good viewpoint. Here, well, actually, first, let's check. Yeah, I don't think it's gonna reach this far. But, like, we could try. Can
No,
you?
If you sit here and your laptop goes here,
Just hear me out.
plug in there.
Hear me out, hear me out. Can you watch and make sure that this doesn't fall?
Yeah.
Thank you. Oh fuck. Yo, it works.
But don't plug it in because now I gotta sit down.
Okay. If this wasn't sus before, now it's sus.
You like return to my.
I love it. Hello.
Hi. I'm gonna sit behind you.
Okay.
So you have space to sprawl out.
Thank you.
This entire row has been occupied by his laptop.
No, also you. And that row is free.
Oh, hell yeah. I'm so excited, are you?
Oh yeah, I'm leaping with joy. If it's
I
not,
see that.
if I know everything, I'm gonna leave like that.
Wait, somebody's
If I
watching?
don't, then I'm gonna cry.
Do you think I know everything?
Oh, I studied.
I didn't. Rip was right.
I went to.
Is that neural network?
This?
No, you.
Me.
Evan, you're
What
like-
what about it?
Evan, you're like a
Yeah.
I know.
Everybody knows him for his neural networks.
From,
You explaining neural networks?
that's literally just you.
Oh well, I know you for that.
Okay.
Well, I know you for that.
Alright, sorry, I'm sorry if that came out rude.
Like,
I did not. You're like, yeah, it did. I'm sorry. Right now I am live streaming this.
What are you live streaming?
this.
Somebody. Oh.
So,
Why?
What do you mean why? It's important. Sorry, that was rude again. Oh my god.
I'm not that easily upset.
Okay. But I'm such a bitch. It's fine.
You want to fight? I'll throw down right now.
I mean, like, not really. Oh wait. Oh, you're talking to her. I'm just gonna like show take. Throw this over there. I'll take care of it later.
Karch, what are you doing, man? Can't start until 9.
We're not starting.
If they read on this one though, I'm gonna be salty as fuck.
They're like holding your.
Wait, is that? Does this do anything?
Evan, you are literally a god.
This literally did nothing. I'm just gonna put it over here.
Just keep shaking.
Yeah, it's fine.
Have you
How
started
many
your
people are
live
watching?
Yeah, there's one. I don't know if I count as one of the people watching.
Here, Evan, I'll watch it.
Okay. Thanks. Why? But
Honestly, you can leave in the process.
yeah.
Tempting.
Oh no.
Ah, no.
That's just testing information.
Okay.
It's okay.
I'll
It's
take a
okay.
picture of it and put it in the group. Oh, nice question.
I don't remember there being an opening in on the last one.
There was no opening on the last one.
Oh. Excuse me.
Hey Dev, the open-ended questions. What are they going to be on?
Me too. Same. No, no.
What else?
Did you do Cal yet? Did you do Cal yet?
Can I name this?
We don't need to honestly give it.
Oh yeah.
So that fucking sucks. Now, did you go 3 full pages, or did you go 2 full pages and on to a third?
4 and a little bit extra.
4 full pages?
No, 3 and I'm on the 4th. Because it only asks for 3.
Okay. So I'm gonna go for 2 pages and then a little on to a third. Because that it's still 2 pages.
Technicality. You know what I think? I'm gonna go sit over here.
Bye. Bye. Bye.
He's being so close. Stop.
Oh, you want me to ask Karch? Karch will tell me.
I mean, you can try.
Karch!
What are you fucking instigating over here?
Is it in culture lock?
No, you are the first now.
You know, I guess.
Tomorrow, 10 p.m.
Wow.
It's like right there.
Yeah.
Wait, oh really?
No, normally people just pay attention to the first part.
Hey Dev.
Yeah, my own cousin calls it side. Because he doesn't feel like parents. No, stop it. Karch.
¿Qué pasa?
What's the open-ended one?
Freaking no.
Also,
Give me the test
What was
are you gonna write on this board or just for that?
No, that's just for the exam stuff.
so was there open-ended on it last year?
Yeah, there's opening on all of them.
Well,
There was not an open-ended
there
on
was
the.
none on the first exam.
And she might not put it on. I don't know. She didn't tell me anything about it.
Okay.
She told me what's like concepts are on it, not what
Okay,
kind of
concepts
questions.
not okay.
Why did she say? What?
They didn't tell you what kind of questions?
No, she told me the concepts of all the questions, not like multiple choice, X through whatever.
Go super in depth with all the Thermochem and Calorimeter.
Plan on it.
What? That's exactly what
I don't fucking know.
Look at the level.
like seriously, you are.
Thanks.
I love when they send me through emails for the past 3 days, and each one of them says reminder to the test.
Like me, honestly.
Who thinks
Ladies and gentlemen, I'll be circulating 3 sign-in sheets. Put your name, ID number, and email, please.
Wait. Oh boy, girl. Okay. What?
Oh yeah, that's
Oh my god.
that's what's his face is.
Me?
What's his face is?
Jim Sloan? I can't call him Jim. I have to call him Jim Sloan. Also, Joan. Because I was introduced to Jim Sloan. I've only ever called him Jim Sloan.
He told me James.
Can you write my name on it? Or actually, I'll just ask them through. Siobhan, can you write my name on it?
Yes, I can.
Like everybody does.
What?
Evan.
Yeah?
EBINDER.
Yes.
Stevens.edu.
Yes.
And I'm gonna need your ID.
Okay, I'll write that because I'm not about to broadcast that to like whoever the fuck is watching.
I got the first 4 numbers for you.
Thank you. You got it wrong.
What?
Can you erase the last one?
How is yours different? Wow.
Everyone that I know has the same 6 digits as me.
I have 104,277.
Okay, well that is also not.
I have 1, 2, 3.
Just keep in mind that everything that you say is probably going to be broadcasted.
Okay, 6.
I'm not gonna remember it.
Okay.
Okay, I'm gonna write it down anyway.
104,236.
Testing, 1, 2, 3.
Wait, can you test that again?
Alright, keep
Wait.
quiet.
Cards,
Oh my
Cards, I
God.
can't hear you. Oh, sorry, Cards, I can't hear you.
Alright, first off, can everybody hear me?
Yeah.
Even people in the back, you can all hear me. And everybody can see everything that's on the board.
Had 10 seconds. Don't tell me all the
Alright, a couple things about your exam tomorrow. Same format as last time, like 25 questions plus a bonus. I believe Dr. Meisner has hinted to me and Karchi that there might be 1 or 2 open-ended. So be prepared.
It's not going to be very difficult.
Open-ended won't be very long. Same exam rooms as exam 1. Alright, go to the same place. They're on canvas. You should be able to see them. Again, we covered chapter 5.6 to 5.10, which are the second half of gases. Chapter 6, thermo. Chapter 7, properties of light. Chapter 8.3 to 8.5, which are the basic electron configurations. And then make sure tomorrow you bring a scientific calculator, a number 2 pencil for the Scantron, and you know your ID number. Dr. Meisner told me that several of you did not know your ID number or put the wrong ID number, which made her life a bit of a hassle to grade your exams.
If you don't know your ID number, you have to wait an extra week to get your exam back. So please just know your ID number and you'll know your grade faster, because that's what causes like the slow process of it. Because you have to go through by hand and figure out who messed up your ID number. Alright, you guys ready to start?
Yeah.
I'm going to start with chapter 5 and then move up till chapter 8. We're going to do all like the worked out problems, all of like calculation problems first, and then move to some conceptual questions. After that, we're going to open it up to any questions you guys have that you want us to either explain some concepts or whatever you guys need, bring example problems. But it'll probably go like an hour and a half for our problems and then a half hour for whatever you guys have left. Sound good? So the first problem, they say a 12.5 liter scuba tank contains helium and oxygen, and they give you the amount in grams of helium and the amount in grams of oxygen, and they give you the temperature. They want you to calculate the mole fractions of each helium and oxygen, the partial pressures of each, and then the total pressure. So first place to start, always just go to moles. That's the best thing to start if you ever don't know what to do with a chemistry problem, is go to moles. So we take helium, 24.2 grams times 4. Always make sure your units cancel. That's like the key to life in chemistry. So you calculate the moles of each. Yeah. 6.05. So you have your moles of each gas. And by definition, the mole fraction of a gas is the moles of that gas over the total moles of gas in whatever system you have. So to calculate the mole fraction for helium, you have the moles of helium divided by the total moles. Yeah. So that's going to be 6.05. That's going to be equal to mole fraction is unitless. That's also important to know. So if you have to use it for anything, it's unitless. So you're going to have to calculate the mole fraction of both of these things anyway to get to the partial fraction, the partial pressures of each. Because if you remember, the partial pressure of any gas is equal to its mole fraction times the total pressure. So now we have the mole fractions, and we want to calculate the total pressure. They give you volume, they give you temperature. They say it's at 298 Kelvin. So obviously you got to go back to PV equals nRT. So pressures are unknown, total pressure. The volume is, I'm just going to solve it. Now you also have the total number of moles of the gas from the partial, or the mole fraction of the gas. So you plug it into PV equals nRT, you get total pressure. Always remember to keep your units in the standard units for it. So liters, atmospheres, moles, and Kelvin. Now that you have total pressure and you have mole fraction of each gas, you can go back and calculate the partial pressure of each of the gases. So you have partial pressure for helium is equal to the mole fraction helium times the pressure total. That's going to be 0.978 times the total pressure, which is 12.1 atms. That will be 11.8. Now, do you have any questions on how to do this problem? Good? The next one we're going to do is Graham's law. Gas A divided by the rate of gas B is equal to the square root of the molar mass of B over the square root of the molar mass of A. Now, in this problem, they tell you an unknown gas diffuses at a rate 4.62 times that of nitrogen gas. So what they're basically telling you is that the rate of the unknown gas to the nitrogen gas is 4.62. They want you to calculate the molar mass of your unknown gas. So, plug in for that ratio of rates which they gave you. Molar mass of nitrogen goes on top because it's on the bottom here. Rate of entry on the bottom. Rearrange this equation algebraically. But if you guys can't see anything that I'm writing, just let me know, especially from the back. So now we have the square root of the molar mass of the unknown equal to this. Square this, square both sides. Now they may also ask you to identify the gas afterward, and at that point you just look on the periodic table and you find which molar mass matches the one you calculated. Any questions on Graham's law? Now it works for effusion and diffusion. It's the same equation. Most of the time they'll do effusion. They might also give you a problem that has the times. So they'll say that one gas diffuses in X amount of time. Find out how much time the other one does. Just assume 1 liter of the gas, divided by the time, and get a rate. Then you can plug the rate into there, solve for the other rate, and then work backwards to get back to the other time. Now on to all of your favorite subjects. Thermochemistry.
Oh yeah, sure. Right here. Yeah. You'll have to put your name down.
Alright, we're going to start with the easy one. So they tell you that a potato cannon, for some odd reason, some kids building a potato cannon, provides a good example of heat and work associated, blah, blah, blah. They say the potato shoots out of the cannon, sometimes flying hundreds of feet. If the burning fuel performs 855 joules of work on the potato and produces 1,422 joules of heat, what is delta E for burning fuel? So first start with what is delta E. You know that delta E is the sum of the heat plus the work. They give you the heat and they give you the work. Now all you have to do is decide what the signs are. So I'm going to draw the table that is in your PowerPoint slides. Real quick. This is like the best table that you can use for this. It's basically to show you which is which, positive or negative. Be able to translate from what they tell you in the word problem to what the sign needs to be in the calculation. So if you have positive delta E, that means that delta E is gaining energy. Simple stuff. Similarly, negative means it loses energy. Heat, if it's positive, it gains heat. Negative loses heat. And W is the tricky one. Positive work means that the system gains energy because something did work on it. So if I push this eraser across the edge of the board, I'm doing work on the eraser and I'm giving it energy. So the eraser, if this is the system we're defining, will have a positive work. Now negative work just means the opposite, that it has to lose energy through the work So that means that the system has to do work in order to lose energy. It needs to put energy into something else. So when I push the eraser, I have a negative work because I'm putting work into the eraser, so I lose energy. So, knowing this, they said that if the fuel performs 855 joules of work on the potato and produces 1,422 joules of heat, what is delta E for the burning fuel? So we define the fuel as a system. They said it performs work on the potato. They said that it produces 1,422 joules of heat. So if burning the fuel produces heat, that means that that fuel is losing that energy because it's being burned and releasing it in the form of heat. So we have negative work, we have negative heat. We get our delta E, which is negative 2277. Now this is important because if you mess up what you're defining the system as, question? What's up? So it says in the problem that the fuel performs 855 joules of work on the potato. So if you're defining, and they're asking what the delta E for the fuel is, which means that the fuel is the system. So if the fuel is the system and it's doing work on the potato, that means that the work has to be negative. Any other questions? Questions? So the potato is actually absorbing the heat from the fuel technically, and it's also getting the work. So if you're going to look at delta E for the potato, it's positive 200 or 2200 joules. All right, we're going to do a thermal energy transfer problem where you have a metal that's put into some kind of water. The metal is at some initial heat. They give you the final temperature, and they want you to calculate the energy transfer between the metal and the water. Don't worry if you just came here for a coffee cup and bombed calorimeters. I'm going to open your minds to a very easy way to do it later on. So in this problem, they say there's a 32.5 gram cube of aluminum. It's initially at 45.8 degrees Celsius, and they put it into 105.3 grams of water, which is initially at 15.4 degrees Celsius. They want to find the final temperature of both those substances once they reach thermal equilibrium. They also give you the heat capacities of both those substances. Or at least it's So, you know, just by basic thermodynamics, heat goes to where there's an absence of heat, right? If you have hot air, it goes to where there's cold air. The aluminum has a higher initial temperature than the water, which means that the aluminum is going to lose the energy here, and the water is going to gain that same amount of energy. So there you can derive the relationship that the heat of the aluminum is equal to the negative heat of the water. You also know that Q equals MC delta T, MCAT. They give you the mass of each compound, they give you the initial temperature. The final temperature is going to be the same. That's the key thing that you need to recognize in this problem. Because once it reaches thermal equilibrium, that means the temperature final is going to be the same. So that's what we're trying to find. You can plug in MC delta T for the water, MC delta T for the aluminum, and you can solve for T final. Because delta T, remember, is just T final minus T initial. So you have 32.5 grams of aluminum times its heat capacity. And always just check your units. As long as your units make sense, then you're probably not wrong. Unless you put a stop. So grams cancel, and then you have T final minus T initial, which in this case is 45.8 degrees Celsius. That's going to equal negative. Well, this side should be negative because the aluminum is losing. Backwards. Yeah, up here. So, distribute this out, you'll end up with like that.
Not supposed to tell them. We don't like the book. So this is what delta T actually is, but I'm just going to represent it by delta T aluminum, delta T water. So I want to figure out what it would be my way.
Also,
well, if you set it up that way and you do your algebra right, you'll end up with 17.3 degrees Celsius. I'm going to try the algebra. You guys understand the premise behind this problem?
Everybody's an angel, a bunny, or like.
Right. The negative and the positive you really can leave up to the end if you want to. Just you have to recognize that the aluminum is a higher temperature than the towards water initially, then the heat's going to leave the aluminum and go towards water. The heat goes from hot to cold. That's just how it happens. Can't change it. So don't worry. I mean, this one you have to worry with the negative.
My mom was a
That's
character from Game of Thrones. Yeah, it's a nickname for the Lannisters. I read the first two.
You guys understand how to do the problem?
Why is it negative QAL?
That's all like the way they did it. The way to set it up is this right here.
And Joel Todd. Joel. He likes this one. He was an advisor. He's an engineer.
So you set up this equation and solve for TS. Yeah, they flip-flop between like the problem. This struggle.
What was the last thing?
Because the way that I'm doing it is different from the way they're doing it. But this negative here, when it distributes, it's going to flip the signs in here, so you'll be right. Right.
Yeah, I know he does that. But I'm going to guess the two guys. Really?
Are you guys ready for bomb calorimetry?
It's like an hour episode.
I don't know, this is just something that people struggle with over here, bomb calorimetry. It's really not as bad as
seasons 3 to 7.
try to experience it.
Not bad.
Bomb calorimetry is actually easier than the Photon calc, there's less numbers.
It's just you know. Why are you here?
So they tell us that when 1.01 grams of sucrose undergoes combustion in a bomb calorimeter, what? The temperature rises from 24.92 degrees Celsius to 28.33 degrees Celsius. They want you to find delta heat for the reaction. They give you that the calorimeter was calibrated in a separate experiment to have a heat capacity of 4.9 kilojoules per degree Celsius. So let's write the givens up. Heat capacity.
They were all from Staten Island.
Yeah. They were all.
So this problem is a lot simpler
trash.
than you might think. What you have to do is look at the units of the heat capacity. In any of the calorimetric problems, look at the units. So in this, they give us units of kilojoules per degree Celsius, which means that if you have change in temperature, you have kilojoules per degree Celsius, you can do swing geometry or unit analysis to get kilojoules. So we want delta T, which is bottom minus initial. And we're going to multiply that by 4.9 kilojoules per degree Celsius. The degree Celsius units cancel. So you go. It depends on if the density is going to be the particle. So you still need a density solution, or they'll just give you the mass of the solution. But so you figure out that there's 16.7 kilojoules involved in this. Now, since it's sucrose, the combustion of sucrose, well, it's not equal. Number P is this. So that's going to be your P equation. U equals delta T times C for bomb calorimetry, usually. 99% of the time. So, since it's sucrose and they said it's combusted, you know that a combustion reaction is exothermic, which means this is going to be a negative heat. Because the water in the bomb calorimeter is higher in temperature than it is originally, that absorbs the heat from the sucrose further, which means that the sucrose has to release energy. So that means that your delta E in the end has to be negative. Now they gave us
yeah. When would you have to convert to kilojoules per mole?
We're going to do that right now.
Oh.
And if you have a question, raise your hands high. I don't know who in the crowd is. So, they also gave us the mass of sucrose we start with. You can calculate the molar mass of sucrose because they gave you the chemical formula. So convert grams of sucrose to moles of sucrose.
They did the chemistry Sunday too.
So you take whatever this is equal to, because they didn't tell me the number, they just did it all together. And you have kilojoules, you have moles of sugar, divide them. So you end up with 16.7 kilojoules over 1.01 over. That's going to leave you with negative 566. Do you have any questions? Good? Bomb calorimetry? So it's negative because the sucrose, when you burn it, is releasing energy. If they would have told you that the initial temperature from the bomb calorimeter with the water in it was higher than the final, then you would know that whatever reaction is going inside endothermic. But usually you use bomb calorimetry for combustion, so most of the time it's going to be negative, not all the time, but most of the time. The next one we'll do coffee cup. Questions?
Guys, we can't hear you. Quiet. We can't hear somebody.
It's negative because when you burn the sugar, it's releasing energy, right? So when you release the energy in the bomb calorimeter, it gets absorbed by the water around it. That's what the temperature is.
We literally just said we go back to
Combustion is usually exothermic.
No, that was bomb.
That's it.
Times your number. People don't appreciate the class.
All right, coffee cup calorimeter, also known as constant pressure calorimeter.
Fuck off.
They give you a reaction.
Now it's coffee cup calorimeter.
That's what I
That
just.
was bomb.
I'm aware, but I was about to change it.
You're really angry.
I am.
Why?
Because you lied.
So they tell you that 0.158 grams of magnesium reacts with enough HCl to make 100 milliliters of solution. and a coffee cup calorimeter. That's just them telling you that it's excess HCl.
Only
Don't
time
have
doesn't
to worry
work
about
out.
it. It all goes to the
Got a pretty nice aspirin.
1 milliliter distribution. They tell you the temperature change of the solution goes
I
from
hope that was caught.
25.6 to 32.8 degrees Celsius.
Don't
Oh yeah.
They also give you the density of the solution. They tell you to use 1 gram per milliliter. And then they also give you C for water, which is pretty much. Now they're asking you to find the specific heat capacity for delta H in the reaction in terms of the magnesium. So we have the volume of the solution at the end, and we also have the density, so we can get to its mass. 100 milliliters of solution at 1 gram per milliliter is 100 grams. You know the heat capacity of the solution. And you also know delta T. So the T final for the solution is 32.8. Initially it's 25.6. That means that the solution is gaining energy, which means that the reaction is losing energy. So if the reaction happens, it releases the heat and it goes into the solution, which is making water. And so we're going to have to use that to figure out whether the reaction has a negative delta H or a positive delta H. Always make sure the units cancel. This is going to be equal to Q of the solution. So remember the units, they give you the heat capacity in joules per gram degree Celsius. So don't mistake that for them giving it to you in kilojoules already. Because usually they'll ask you to convert it to kilojoules in the end. So the 4.18 number, whenever they give that to you, it's usually joules per gram degree Celsius. So watch out for the units. Now we know that Q solution is equal to negative Q reaction. Because like we said before, if the solution is gaining energy, that means that the reaction is losing energy. So if we have this much energy coming from the given mass of magnesium, we can convert that to moles of magnesium, and then we'll have delta H for the reaction, and joules per mole, we convert that to kilojoules.
Guys, we're passing around those sign-in sheets, right? We're all getting around, right? Because I have a PowerPoint for my section, and so I'll be trying to send that out to most of you guys tonight, so you have a little bit of that. Cool. Anybody else not get this?
That was
Put that in the description.
It's crew
What?
The PowerPoint.
Yes, I know. I was gonna do food.
Walker's right.
So, 200%.
The only bad part is the scent. It smells like that. It's a really gross review.
It's high quality.
Is that what you guys call it in Jersey?
Yeah. What? was showing the.
So, how much did that webcam cost?
I just found it in my house, and I was like, this would probably come in handy.
Does everyone understand how to use Pro? So the question says, I'll read it word for word. In an experiment to determine the enthalpy change for this reaction, 0.158 grams of magnesium metal is combined with enough HCl to make 100 milliliters of solution called the ductile residue. The HCl is sufficiently concentrated so that the energy can create the reaction. That just means that all of the magnesium reacts, so that means you don't have to worry about any excess. The temperature goes from 25.6 degrees Celsius to 32.8 degrees Celsius as a result of the reaction. Find delta H of the reaction. Use 1 gram per milliliter as the density of the solution, and the heat capacity of the solution is 4.18 joules per gram degree Celsius. They could just ask you for the heat involved, yes, or usually they ask you for the heat. Right. H is conventionally filled with So they give you that it reacts and forms 100 milliliters of solution, and they give you the density of the solution so that you can convert that volume into mass. So if you have 100 milliliters of solution at a density of 1 gram per milliliter, you have 100 grams of solution. Then you can use the heat capacity equation, Q equals M double T, MC double T. Question in the back. I can't hear you. Negative 460 kilojoules. That came from negative 4.6 times 10 to the 5th joules. It's negative because the reactant is releasing energy. So that means you know that if the solution is gaining, the reaction has to be losing, vice versa. Right, so the temperature of the solution rises, which means it has to gain energy. Which means that the reaction loses that same amount. Alright, we're going to do a Hess wall column next.
Lift your computer off. The intake fans are on. It sounds good.
So they give you this reaction that they want you to calculate delta H in the reaction for. So they give you a couple intermediate reactions that you can use to figure out delta H for this reaction. The first one they give you.
Saturdays and Sundays, if you want us, partially.
So they give you these three thermochemical equations to figure out the delta H in the reaction above. So to do this, you have to use Hess's law, which basically is like adding and subtracting equations, like thermochemical equations to get to a specific goal. Now you can do a couple different things to thermochemical equations. If you reverse the reaction, you have to switch the sign of the delta H. So you can flip this reaction up here, the combustion of propane. If you flip the reaction, you have to make sure you flip the sign of delta H. You can also multiply or divide the entire equation to give it different coefficients. You can multiply that second one by 2 or do whatever. But what you do to the equation, you have to also do to the delta H. So it comes down to a point of trying to manipulate these three equations so that when you add them all together, you get back to that top equation. In doing so, all those manipulations that you do for the delta H values will follow through, and that final delta H is going to be the delta H for that top reaction. So what I like to do is to start by looking at what only comes up once in any of the equations we give. So O2 comes up in all three, so you don't want to try to balance O2 first. Carbon only comes up in one. Propane only comes up in one. So I'm going to write the steps down on the bottom board. So you see that on the top reaction, the propane is on the right side of the equation. The one that you're given, it's on the left side, which means that you have to flip the sign of delta H and flip the reaction. So when you flip it, you end up with 3 CO2, 4 H7. Rewrite the new delta H value so you don't forget.
I suggest that if there is a blank sheet of paper on the exam tomorrow, whether it be in the back of the formula sheet or the exam, to do the Hess's law problem, do not try to cram it all into the little space that you're given.
Now we have this on the right side. We need carbon on the left side. It's already on the left side. But in the equations they gave us, we only have one carbon. The equation we're trying to get to, we have 3. Which means you need to multiply that equation by 3.
Yes, same cover sheet that was on last year.
So remember, to multiply the equation by 3, you have to multiply the delta H by 3. Now for the last one, you're trying to get rid of all the oxygens on the right side and get rid of all the waters on the left side. Which means that you need to have water on the right side for the last equation and oxygen on the left side. We already have 3 oxygen, which means we need 2 more to balance that out. We have 4 H2O, and conveniently, there's 2 H2O already on the other equation. So by multiplying that third equation by 2, leaving it as it is, just multiplying it by 2, we'll end up with enough oxygen on the left side to balance out the oxygen on the right side. Similarly, we'll have enough water on the right side to cancel out all the water on the left side. Now we did all the manipulations to the equations. We need to make sure that everything cancels out that's supposed to. So I have 2 O2s. On the left side, cancel the 5 O2s on the right. So top equation, 4 O2 here, cancels out 4 O2 here. 3 CO2 here, cancel that 3 CO2 here. We're left with 3C, 4 H2. Now the delta H for this reaction is just going to be the sum of all of these. So with Hess's law, start with the things that only appear in one of the equations. Start and put them in the right place and balance the coefficients that you're supposed to get, and then work from there. So move to the next, like least occurring thing, and move all the way down until you're most likely just balancing oxygen, CO2, which are the most common things that show up in most of the equations. Yeah, they're not going to be
But some equations might not. All right. That way, using that, you're going to have to look at the overall reaction of the and then it's a puzzle. There's no one way to work it out. You got to look, and you've got to see, okay, if I look this, or if I multiply this,
This is only fun we don't
that,
know.
how do you get the puzzle?
We're moving on to chapter 7. We'll do photon energy. So we're given that a pulse of light has 3.83 millijoules. That's also equal to 3.83 times 10 to the 36. They also give us the wavelength of the light. And they're asking you to find the number of photons that the light contains. So to do this problem, you need to figure out the energy of the pulse and the energy of an individual photon. And using that, you can figure out the number of photons. Figure out the energy from the pulse. Figure out the energy from the photon that's emitted with that wavelength. You need to use this equation.
8 a.m. chemistry, and then Wednesday in graphics.
So the energy of the individual photon that's emitted
Every day
is
we
equal to Planck's constant times the speed of light over the wavelength. Everything that you need to plug in everything in the standard units. Since this is physics, light is physics, and not chemistry, you need to use meters. You need to use kilograms, and meters per second is up the back. Yes.
It's me every day.
Very good.
Chemistry.
So lambda, the wavelength that's in nanometers, that's 10 to the negative 9. No question? Right.
Do you have a night class? Today?
If you plug it in nanometers, you're going to be off by a factor of 10 to the 9.
Ryan, who's tall and wears a blue one all the time.
You have to get right in.
He's there.
So you know Planck's constant, you're going to be given this on the sheet. It's never going to make you memorize constant.
Doesn't say a lot, but it's not actually. Effortless. Cal is my worst class.
He's like,
Got a B minus in my first essay. And a B plus in my midterm.
So this gives you the energy of that individual photon from that light. Questions? Why? This one? This is the speed of light. So the speed of light is 3 times 10 to the 8th meters per second. This one? Very short. It's Planck's constant. 8. So you get the energy for the photon.
Do not talk about this.
And that's
the other one
on
that's
my
the
screen.
individual
And the
photon.
last one
So
is
it's this many joules per photon.
something else. The microscope. Those are the 4 Cal teachers.
No politics on my screen.
No, that's what the Cal teachers are teaching.
So now you have the total
One of
amount
the
of
Cal
energy
teachers were
that
doing on
goes light,
gender, the other one's
which
on
is
women and
energy for
oppression,
the
the other
pulse,
one's on descent.
divided by the energy per photon. So that's going to give you the number of photons. It's just unit analysis. But if you divide it by this, you're just multiplying it by 1 photon over that number. So, we have
The energy equals HC over line. Have the energy. If you have the energy, you have that's the energy per photon. So when they give you a total energy, and you find the total.
you end up with a lot of photons. So the last part,
Yeah, it's just constant.
so E in that
It's
equation is
just
Planck's constant
Somebody was
Yeah.
doing math and they said if I
Finding the
multiply by
energy
this,
per
so
photon.
you have a constant.
because it's the energy of the individual photon. So you can interpret that as the energy per photon of that light. So if they're saying that the pulse of light has a total of 337 milliseconds of energy, and we know the amount of energy in a single photon is what we calculated with that equation up there, then we can use unit analysis to figure out the number of individual photons. Any other questions? Does anyone not understand what I did? Alright, so the next one we're going to do is the Broglie Wavelength one. Yeah.
You're a double major or major? Double major? How many credits? How much you take now?
I don't know. How do you spell the Broglie?
B-R-O-G-L.
No way.
It's Broglie.
So they give you the speed of an electron in this problem, and they're asking you to calculate the wavelength of the light that is emitted. So they're telling me V is
I'll take this upstairs.
So with this one, you want to use the Broglie wavelength equation. That basically relates the speed of the electron to the wavelength of the light that it emits. So the Broglie's equation, lambda H over mv, where H is Planck's constant, m is the mass of whatever you're dealing with. In this case, it's going to be an electron. V is the speed. Like I said before, since it's physics, if you're going to look at the mass, it needs to be in kilograms. Length needs to be in meters. Speed needs to be meters per second.
That's not V.
And energy should be in
That's
joules as well.
frequency. That's frequency. I mean V.
It should, right? So you have to look at the energy change from the state that the electron is jumping. So the energy change of the atom by that electron moving is going to be the energy state from one orbital shell that it was in originally to the one that it moves second. They give us that?
No, actually.
Yeah. Good part on the outside. No, they're both going to do our best. Look, you get better than 100, I wouldn't be impressed. You get that extra credit? Proud of you. I mean, because I'm
Or you could also use
get
this
100,
one.
you get better than 100.
So this is the one that was in your recitation that they had to write the equation on the board for.
You have this. This one you get. You definitely get this one.
If you need to use this equation, they will give it to you on the formula sheet. I didn't know. Trying to find where they tell you.
It's not like this. This is a due tomorrow. What's yours?
Oh my gosh, I here's your whole conversation.
Alright, so the PowerPoints that I got kind of sucks, so I'm going to have to do this one on my own. But the Broglie equation, this one, it links the wavelength of the light to the speed of or the wavelength of the light emitted by the electron moving to the speed that it's moving. So if we're trying to solve the lambda, we plug in Planck's constant here. They say it's an electron, which means that you'll be given the mass of the electron in the table, and they give you the speed in meters per second. Now this result will be in meters, so if they want you to put it into nanometers or whatever it is, nanometers is kind of 10 to the negative 9. Now, so the Broglie is a simple equation, simple plug and chug problem. Make sure that your units are right. Anyone have any questions? So that's what they messed up the order in PowerPoint. So the last one, chapter 7, we're going to do is looking at the wavelength of light when an electron jumps from one energy level in the atom to another.
What did he say the subject was? What did he say the subject was?
You just said when an electron was going to jump from one to the other.
Is there a name for that?
So the other version, so wavelength transition, it's basically saying that when an electron jumps from n equals 1 to say n equals 2, it's going to emit some kind of light, releasing energy. So there's an equation that you can actually use to calculate that. And
was the one over minus the one over squared minus 1
And I squared. I think that's
that was
this.
times a constant.
That was time stuff.
So they give you that a wavelength of light is emitted from an electron making a jump in a hydrogen atom, and it goes from orbital n equals 6 to n equals 5. So those are the two givens that you have. That is initially at n equals 6, and it jumps into n equals 5. And they want you to find the wavelength of the light. So, since we're starting at 6, that's our initial energy state. We're trying to find the change. So you take the final energy state minus the initial. In this particular equation, you're taking the inverse of the square. So it ends up in 5, which means that that's going to be the first one that you put in the equation, minus the 1 over the 6 squared, which is the initial energy state it's in. And this equation is going to give you the energy of that light that's emitted from the electron making that energy change. And it's going to be really small. Now step 2 is you take that energy and you plug it back into this equation. And you solve it for lambda and calculate lambda. Because that's what they're asking you for in this equation. There's the problem. Right. So with these types of problems with an electron moving from one energy state to another, you need to figure out which energy state it starts in, which one it ends in, which is given to you. It's final minus initial, almost always, whenever there's a change. And you use this equation, the top one, to calculate the amount of energy that is released by that photon of light. Then part 2, you take that energy and you plug it into the equation on the right to calculate the wavelength. Usually you'll be able to figure out what equation you need based on what you're given. So there's always going to be some number of unknowns, and then, or only one unknown, and then the rest of them are going to give to you, or give you things that you can use to solve for it. Are there any questions? If you need to use it, it should be on the sheet. It wasn't on last year's sheet. On the live video, let's touch on it. Question back?
It goes away.
It just goes away because wavelength can't be negative, positive. So just interpret that like you can't have a negative either.
Somebody asked a
You don't have a
question
positive
one
either.
night. He needed his answers on it.
Oh,
All right, so I'm going to take you through some of the conceptual section questions for this exam. So I'm going to start in Chapter 5, and we'll make our way down to Chapter 8, which will be the Electron Configurations. So, what is the main factor with determining rates of effusion and diffusion? There's a problem on it, but it's this is the main factor. This is the point where you guys participate. Molar mass, yes. Molar mass, remember, it is, in order to find the rates, you have element A over element B, square root of molar mass of B over A. Which of the following would have the highest ratio of effusion? So which of the following, if you were to do the Graham's law calculation for, would it be highest? Shout them out. I hear A, I hear B. C. I hear B. A lot of B. C. All right. All right. So the highest ratio would come from the two that are the furthest apart, right? Because the molar masses, the ratio of the molar masses would be the highest over the lowest, which means the highest number. Therefore, the correct answer is B, because helium and argon are the two furthest apart in terms of molar mass. Everybody understand that? Everybody can do a Graham's law calculation tomorrow? So what are some of the ways to make a gas behave more ideally? There's real gas, ideal gas discussion. Raise the temperature. Austin? Standard temperature. Not standard temperature. So, as we just got here, we want to increase the pressure, increase the temperature, or decrease the volume. And why? Because as the values of A and B in the van der Waals equation approach zero, what happens to the behavior of the gas? It becomes more and more ideal. A and B, if you look at the van der Waals equation, which I'm not going to write it, but remember that it's B minus A, I know it's not, it's A squared, but, and then B minus B. So as A and B approach zero, P and B become more like their ideal values, just like the ideal gas.
Question?
That's how, I'm just asking how you could get it to be a real gas to become more ideal. You're right there that ideal pressure is high temperature, low pressure. Just asking how you can get a real gas to be more ideal. So bad. Yes, this is what I always said. Yes. And all the problems that Karchi did are under the exam 2 PowerPoints. You can look at them via there. I'm going to send this to you in an email. You don't have to write it down. Go ahead and write it down.
Is this over? Oh. Wait, this is I'm so confused.
Father Bob. Which of the following has the highest kinetic energy at 300 Kelvin? Who thinks it's A? Who thinks it's B? Who thinks it's C? Who thinks it's G? Who thinks the answer's not up there? The answer isn't up there. Good question.
They're all the same.
At the same temperature,
Oh,
all gases have the same kinetic energy, the same temperature. Read the questions well. You're probably going to get one of these. It's either going to be this or this, which has the highest velocity at 300 Kelvin.
Lightest molar mass.
The lightest one, which is helium. Remember, again, at the same temperature, all molecules of gas, regardless of mass, have the same kinetic energy. But what differs, because their masses differ, their velocities will differ. And so the one with the lightest mass has the highest velocity because they all have the same kinetic energy. Oh. About a minute. Go. Guys, I can't hear the guy in the back. Higher velocity would lead to more collisions, would be higher pressure, yes. Please read the question. Read the question carefully. A couple of ThermoChem questions. Just a little review. What is Q positive and Q negative? Yes. And Q is negative when it's exothermic. Or when heat is absorbed, it's positive, and heat is released, it's negative. Same thing. What is work positive? Work is done on the system. Work is negative. Work is done by the system, on the surroundings. If a system releases 40 kilojoules of heat and performs 28 kilojoules of work on the surroundings, what is the total change in energy in the system? Everybody raise their hand.
No. Oh, yes.
Negative 68, yep. Everybody understands this, right? Delta H is positive when it's endothermic, heat is absorbed. Delta H is, sorry, Q. Q is negative when heat is released, exothermic. Work is positive when work is done on the system, work is negative when it's done on the surroundings. This one, think about it. Two samples, A and B, have the same mass, and they absorb the same amount of heat. However, the specific heat of A is 2 times that of B. The initial temperature of A is 20 degrees Celsius. The initial temperature of B is 50 degrees Celsius. The final temperature of the system will be 10 degrees.
It's going to be
Substitute rapid, move things around. They are. Maybe some of them. See. All right, just take a poll. How many of you think it's A? How many of you think it's B? How many of you think it's C? All right, good. At least you guys didn't pick B, not B. So, we have the fact that Q's are the same, right? MA also equals MB, and 2 times the specific heat of B equals the specific heat of A. So if we relate the two, QA, MA, sorry, CA, MA delta TA equals CB, MB, delta TB, right? We know the masses are equal, so we're going to get rid of them. We also know we can also replace CA with 2CB. So we have 2 CB, delta TA, CB delta TB. Now we have CB on both sides. Get rid of those, which means 2 times the delta T of A equals the delta T of B, which means that the change in A is going to be less than the change in B. So, given the fact that A is 20, it's going to gain some heat because 50 will come down. So they're going to meet at some point in the middle. And because we know that 2 delta TA equals delta TB, the answer should be between 20 and 35. More specifically, I left this up, I let it generalize the answer, but you can kind of figure this out right away with 2 TF minus 20 equals TF minus 50. And you can see that the delta TA will equal 10, and delta TB will equal 20, and they'll meet at 30 degrees Celsius. Question? Yes, technically there is a negative here, but you go through it, you'll see that we have 2 TF minus 40 minus TF plus 50, right? 3 TF equals 90, the final is 30. Right? So I think this is a good problem to just see how the relationship between the 2 specific heats, if you get a problem like this on the exam, so you know you can check yourself. You get an answer that's towards one side, you know that you go with the higher specific heat will be on, the element with a higher specific heat will have a less of a temperature change. All right, this is a tough one. This one wasn't tough. Can you measure H enthalpy directly from a bomb calorimeter?
No.
Why?
Measure
Not measure the constant bomb calorimeter first. 2-step process. What is a state function? What is a state function? Only depends on its final state and its initial state, right? We don't care about what happens in between. For all of these reactions that we've been doing, we haven't been showing you it, but there's something called activation energy. I don't know if you guys have heard this in high school chem. But basically, this is the initial energy here. This is as time goes on. Initially, we have to give the system an influx of energy in order to get the reactants to react. And this distance here is the activation energy. But since energy is a state function, we only care about what happens at the beginning and the end. So this right here would be delta T. So besides energy, what is the other state function that we've learned in this chapter? Work and heat are not state functions. Don't get that wrong like I did last year. Can't measure H directly, but I haven't done a lab yet with bomb calorimeters.
You have to do a calibration.
You have to do a calibration test to find the constant of bomb calorimeters. And then
Basically,
you
burn
find
something
the
and
energy.
you know how much energy is in it. Measure the temperature change, and then you get
You burn like a
calibration.
steamer. Is work positive or negative for compression work? Work equals P delta V. Compression, the volume decreases. Does that mean work is positive or negative? Negative. In expansion work, volume is increasing, which makes T final greater than T initial. So work is positive. And very simply, how do we determine if a reaction is endothermic or exothermic?
So the energy inside it loses energy and the chemical inside it is. Okay, so energy goes.
Yeah, I'm wrong.
No.
Yeah, don't listen to me.
It's the other way around.
It's the other way around. I'll change it when I send it out to you guys.
So if you have a balloon and you put compression on the balloon, the volume is going to decrease, which means it's going to be positive work. If the volume decreases, that means your final volume is less than your
Are you
initial.
serious?
Two negatives will cancel out, and the compression work is positive. But you have to do work on something compressing. The opposite, expansion work, is trying to expand the walls of the balloon with gas. So the gas is doing work on the inner walls of the balloon. So it's negative. Because the volume gets bigger, delta V is positive, work is negative V delta V.
What's up? Maybe 1 or 2. Maybe. We don't know. We didn't see the test. So,
We don't even get to see them after you.
photons. Remember, they're packets of energy. As we discussed in the earlier problem. Yes. So as a hydrogen atom moves from n equals 2 to n equals 5, is light absorbed or emitted? Absorbed. And moved from n6 to n1, it's emitted. What was the result of the Broglie experiment? Particles of wave-like behavior. And describe the relationship between electron energy, frequency, and wavelength. And what's the constant that holds frequency and wavelength? Yeah. So, what are the possible values for the quantum number n? All positive values, 0 to infinity. What are the possible values for L? 0 to n minus 1, yes. Possible values for the magnetic L? Good, and the only two values for MS? Plus or minus a half. What do each of these variables mean? N, what is N? Principal quantum. Yes. N can be 0, yes. Yes.
We were taught that again, but like, that's fine.
We don't care about that though. We start at 1. We're in America. We start at 1. You ever gone to Europe? You ever gone to Europe? The first floor is technically 0. America, we start at 1. L, what does L stand for? What does angular momentum define? Orbital shape.
N equals 0 doesn't apply.
You want to say that out loud for everybody to hear?
L, so you're not taking tomorrow because you can't this exam.
Yes. We're not too sure about that.
Shut up, Dad.
We're at energy level 4. How many orbitals are there in energy level 4? Yes. How many electrons in energy level 4? It's full. 32. Good. All right. Time for some electron configuration practice. Go ahead and
Oh my God.
Electron.
No.
Time to write electron configuration. Yay.
What?
And the mass exodus, because this is a really easy topic.
Is this the last?
This is it. We have 2 more slides. That's it. This one and one more.
After this, we're going to open it up to any questions you guys have on any concepts.
While you all are headed out of here, I'll send the conceptual PowerPoint email. Some hopefully by 12:30, 1 o'clock this morning, tomorrow morning. I'll also throw the PowerPoint some parts you use to get us tested, questions. You'll have it all there for you.
Okay.
All right, who wants to give me the noble gas configuration for selenium? One. Good job. Argon, good. 4s2.
3b and 4p4.
4p4, yes. Noble gas configuration for bromine. Argon.
4s2, 3d10, 4p5.
Good. I didn't realize I particularly put these two next to each other. Potassium plus, just the noble gas configuration.
Neon.
Argon. How many valence electrons does K plus have? None. How many valence electrons does chlorine minus have? No, not 0. 8.
Where are they?
Remember, a cation that goes down to a noble gas has lost its complete outer shell. An anion that goes to a noble gas has gained its full outer shell. We can tell by the electron configurations. And then potassium 2- ion. No. That'd be 3-. I tried to trick you.
That's phosphorus.
Phosphorus 2-. Neon. 3s2. 4b5. All right, the next 3 are the tricky ones, or not so tricky ones. Depending on which way you want to look at it. Chromium, and technetium. Each one of these has kind of a special trick to it.
Oh, shit.
Extra credit. Exciting question.
Oh, these are the Fs.
Why?
It's F. It has an F. Give me extra credit. Oh, question. Hey Dev, are we gonna have to do like with the transition metals?
This is exactly why I'm giving it to you.
Okay.
Exactly why.
I thought these were the.
Each one of these has its own kind of little thing I want you to think about before you write the configurations. There's the anomalies, or well, 2 of them are. The third one I put in make a difference.
You want the noble gas configuration?
It's just raw by itself. It's just raw.
Oh, I made it.
8 a.m. lecture, I don't expect you to show up tomorrow.
Photon.
Because it's 8 a.m. and its class is optional. I don't expect you to show up. What if even 9 a.m.? I don't think you should show up. Do go to class if you want, if you do have questions.
We're not telling you not to go.
We're not telling you not to go to class.
Honestly, I
This
wish
was
I had
class. No, this is class.
I wish I had these guys.
You want the configuration?
I just want the noble gas is fine. All right, let's get out of here. Yttrium, noble gas configuration.
Photon 5s2 41.
5s2, 4,
41.
4. 41, right? Yes, 5s2, 41. Chromium. Argon.
You gotta know chromium. I can almost guarantee it's gonna be on the test.
What number should I put after S
They
and
will
D?
ask you what the electron configuration for chromium is. Have you done those steps?
1 and 5, yes.
That's the next point.
Why? We looked originally. We have 2 in the 4S. 4 in the 3D. This is not a stable configuration. However, we move 1 from the 4S into 3D. That's stable because each orbital is at least partially filled. Now, is this paramagnetic or dimagnetic?
Oh.
No.
Does anybody hear this? Did you hear this term?
No.
Dimagnetic?
That's
How the
not
hell
on
have they
there.
not
That's
heard
not
that?
on there.
It's not on the test then. Technetium.
What is the
Literally.
symbol?
I just got so much more.
5s2 3 5.
5s2?
45.
45, yes. But for technetium, when it's 4d5 originally, we do not move any of the s electrons over. Does everybody understand that? All right. When it's originally 4s2 3d4, right? Is that the top diagram? That is not a stable configuration. We would rather see all the shells partially filled then one filled and one is completely empty. So what happens is we take one, we steal one from the 4s, and we throw it in the empty 3D. However, in Technetia, when it already has 5, there's no need to pull out an extra S electron. All right, question. What? If it's 3D9, you do the same thing. Yes, pull the 10. Valence electrons? Or which one? 1 and 2. We only look at the outermost shell is valence electrons. So n equals 3 is less than 4, right? ML, very arbitrary. All right, ladies and gentlemen, you can come down here and talk to us if you have any more questions. Good luck and Godspeed tomorrow. Thank you. We'll see you. If any of you have Chris Motto for TA for California, you know what I'm saying.
Evan, you gonna go to your chem class?
I don't know, probably not.
Fine, when's yours?
Mine is at 12.
I would be.
You would
I'm not
go?
going to my 1 o'clock.
Wait, you said that you would go to 12, but you're not going to 1?
No, I wouldn't go to.
Oh, yeah.
I wouldn't go to 12 because I wouldn't go to 1.
Okay, sure. I've been recording for...
I'll be up until like 2 a.m. doing my paper.
I'll be doing something at 2 a.m.
Yeah, but you know what? Like I said, I'm going to do 2 full pages and then a little onto a third. Because you know, cheating the system there. Plus, what?
Oh, damn. I have to do, I have to start my engineering design essay.
Oh, damn. Yeah. Yeah, I haven't done that. So. Yeah, Evan, I don't think anyone's asking questions.
I mean, I don't think they're writing it on the board. Something went wrong. Did it crash? Or is it just my phone? Oh, it's just my phone.
Evan, you are literally a god. No one else would have done this.
Like and subscribe.
I will. Like and subscribe.
And pay my tuition. I'm in so much debt.
Please help Evan. And get 100 on your chem because you're watching this.
Yeah. If you see this, Antonia, and I know you're watching, you better study. Also, I love you. Oh my god, some guy was just vaping. What? That's so lit.
What?